Okay, so an explicit function, we can express y as a function of x. And we can get y by itself. Okay, so example of an explicit function, y equals 1 over x. It's also on the paper. So this is an explicitly written function. Okay? An implicit function is not necessarily written with y by itself. So I can write this equation is in explicit form. I can write it as f of x equals 1 over x. So when we say something like f of x is called function notation. You've probably first learned this in Algebra 1. F of x replaces the y as the variable we use for the output, because this allows us to say like that f of 1 means I'm putting 1 in place of the x, so that would tell me I put 1 in for x and work it out. Whereas it's a little bit harder to do, you have to write like more. You have to say find the value of y for the function 1 over x when x equals 1. So this is just like a shortcut version. But f of x represents y. When we say f of x, the function's name is f, and it's telling us whatever letter's in here, it's saying, hey, that's the variable you're dealing with here. So that's what we mean we can express y as a function of x. Explicit function, the functions you're used to dealing with. An implicit function is one that you cannot, it's like taking this equation and multiplying both sides by x and writing xy equals 1. This is an implicit function, okay? And yes, this implicitly written function, I can get y by itself, that's fine, okay? But this is just the implicit way to write this explicit function. So these two functions are the same thing, okay? They're exactly the same thing. One just has y by itself, one does not. Like you've had linear equations, like a linear equation in standard form, 3x plus 5y equals 7. This is a linear equation. This is in explicit form or implicit form because y isn't by itself. Okay, you might have dealt with equations of circles. X squared plus y squared equals 9 is the equation of a circle. Okay, this is the easier version of the equation of a circle, because if I were to write this circle equation in explicit form, when I go to get y by itself, first I'm going to subtract x squared. And then I would have to square root both sides. When I square root both sides to get y by itself, it causes me to end up with two functions to represent this one implicit function. Because when you take the square root as a way to isolate a variable, you have to add a positive and negative. So this equation would require both the positive square root of 9 minus x squared and y equals the negative square root of 9 minus x squared in order to get the full graph. Like this is an equation of a circle who's centered at the origin with a radius of 3. And that's easy to tell in this implicitly written circle equation. Okay? It's easy to find the graph from that. If I got y by itself, it takes both of these equations. I would have to graph both of these to get that full picture. This would be the top half of the circle, and this would be the bottom half of the circle. So there are cases when implicitly written functions are more useful and faster and easier to deal with. There are also some equations where we just cannot get y by itself. A circle is an example of a conic section. So other conic sections are ellipses, hyperbolas, parabolas. Okay? And all of those have nice implicit forms that we use more often. And there is the general conic section formula, which is like ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. This is called the general conic section. Yeah, so that should have been a pre-calculus topic, but maybe it wasn't. So like in this case, I can tell that this is a circle because the x squared and y squared have the same number in front, like a and c. But my whole point of writing this is like this type of equation. Notice you have an x times y term. You are not going to get y by itself here. I mean, why would you try? Okay? So what we need to be able to do is we need to be able to take derivatives when equations are in implicit form. So we need to be able to take derivatives from this form, okay? And it does take the knowledge of the chain rule, because whenever we take derivatives, we're taking the derivative in terms of x. This means the derivative in terms of x. When I write y prime or f prime of x, it still means we're taking the derivative in terms of x, okay? It means that the variable we're taking the derivative of is x. And so like another way to write the derivative is dy over dx, the derivative of y in terms of x. The dx means in terms of x. So if I'm taking, say, the derivative of y, okay, and this is like the key thing here for doing this, the derivative in terms of x of y, well, what the heck is that? Well, we have to treat y as an unknown function of x. Kind of trying to give you the rationale behind why we have to do what we do here. So we need to treat y as an unknown function of x. So for every time you have a y that you're going to take the derivative, I'm just taking the derivative of plain old y. If I want to take the derivative of y in terms of x, okay, I have to think like the derivative of y is like the derivative of the outside. So the derivative of a variable by itself is 1, right? Like the derivative, what's the derivative of x? 1. So the derivative of y is 1, but this is not in terms of x because I took the derivative of y. So this was like the derivative of the outside, so this is like the outside prime, multiplied by the inside prime. So the derivative of y is dy over dx, or y prime. And so every time we take a derivative of something that has y in it, so let's say I had let's say I was just taking the derivative of y cubed in terms of x. So let's say I wanted to take the derivative in terms of x of y cubed, and we have several of these to look at on the examples. The derivative in terms of x of y cubed, well, the outside function is something cubed, and the inside function is y. So the derivative of something cubed is 3 times that something squared, and that something is y, times the derivative of y, which is dy over dx. And I do, like you could write y prime, and I think the solution manual writes y prime. I tend to recommend that you write dy over dx so that it stands out from the y's, okay, because we'll have another process we have to deal with. So this is just finding the derivative of just like a term or something. So I went over pretty much this stuff here. When differentiating with respect to x, any term with only x variables will be differentiated normally. Any term with a y or another variable must be differentiated using the chain rule, as I just talked about, because it is assumed that y is defined implicitly as a differentiable function of x. So I'm just going to, we already did this one. Like this one would be, I'm not going to write, I shouldn't write in this here. So we already did number 2. So the derivative in terms of x of y cubed would be 3y squared times dy over dx. Or you can write 3y squared multiplied by y prime. Just make sure you can tell the primes from the y's. All right, so the derivative in terms of x cubed. Well, this is fine. This is just a normal derivative. This is 3x squared, okay? All right, how about this one, the derivative in terms of t? So this is read as the derivative in terms of t of v. All right, well, v is a single variable. What's the derivative of a single variable? 1 times the derivative of v in terms of t. That's how I recommend you write it. All right, let's move down here. The derivative of x plus 3y. All right, well, this is the same as taking the derivative of the x part plus the derivative of the 3y part. And if you look at the PowerPoint presentation, if you go through the PowerPoint presentation, they show like all of these steps. They show the problem, They show that we're differentiating each part with respect to, sorry, that should say dx. I don't know what the heck. The derivative in terms of x and the derivative in terms of x of 3y, and then they take the actual derivatives. So the derivative in terms of x is just 1. And if you think like it's dx over dx, okay, the derivative of x in terms of x, well that cancels, that's just 1. Okay, so this derivative is just 1 plus the derivative in terms of x of 3 times y. So we first think the outside function is 3 times something, okay, so that derivative would be 3, and then you multiply by the derivative of the inside, which is y, and that's dy over dx. So the derivative of x plus 3y would be 1 plus that. All right, so now, what's the derivative of this? Well, the first thing we have to recognize is this is a product. This is a product where I'm going to say x is the first and y squared is the second. So when I take the derivative using the product rule, I'm going to have to go first times derivative of the second plus second times derivative of the first. Or it could be this. F prime time, I mean, I don't know how you have it memorized, but these are all the same. Like, these are all the same thing. It's all the same rule. I've taken the derivative of both parts times the other. The derivative of each part times the other, regular. Okay, so I just wrote out the rule. So this derivative, the derivative of the first, or so I write the first, which is x. Okay, I'm just writing the first. The derivative of the second, the derivative of y squared, well, chain rule, the derivative of the squared part is 2y times the derivative of y is dy over dx. Like, I always just think when I take the derivative of a y part, I take the derivative and then multiply it by dy over dx. Anytime you take the derivative of a part with y, you then multiply it by dy over dx, or y prime. Outer is the derivative of the y part, inner is just the y prime. So this is first times derivative of the second, plus the second, times the derivative of x, which is just 1. When I don't need the y squared, I didn't take a derivative, so I can just write y squared. Now, I would just clean this up a little bit, and I would write that 2xy times dy over dx is equal to, plus y squared, not equal to. You could factor a y out of there, you don't have to. Now, this is just differentiating a statement and not a full equation. So we usually don't, I just start with this to demonstrate a little bit of how to do implicit differentiation. But in reality, we're going to be differentiating equations. So there are steps on the bottom, but I do want you to look at the problems on the top of the next page. So these are the problems that we're going to look at, and also the steps here. So this is what we really want to be able to find the derivative of. And I'm not going to try to get y by itself. At no point should you make an attempt to get y by itself here. You're not going to. It requires very advanced algebra. Plus, it's just going to be faster to take the derivative implicitly. So, when we take the derivative implicitly, we want to follow the steps at the bottom of the previous page. We want to differentiate both sides of the equation with respect to x. So, that's like when you take the derivative of the y part, you have to take it and then multiply by dy over dx. Everything on both sides, just left to right. Then, we're going to have to get dy over dx by itself. So once you've actually done step 1, you've done the calculus part, like you took a derivative. So the only calculus part of this is differentiating both sides with respect to x. But then our goal, from here, we need to now get we need to get dy over dx alone. Because our goal is to find the derivative of y in terms of x. And we want to have it so that it's by itself. And so these next 3 steps are just the algebra process that you go through to get it by itself. And they will work every time. Collect all of the terms involving dy over dx on the left side and move all the other terms to the right side. Then on the left side, factor out the dy over dx and then basically get it by itself. And it usually just requires some division. Okay, so I'm going to follow these steps in these two examples here. So this is probably the easiest example. I'm just going to write this bigger. So, when I take the derivative of everything on both sides, none of these, I treat each term separately. I'm taking each term's derivative in terms of x. So the derivative of y cubed is 3y squared times dy over dx. Or just y prime is fine. And then the next term, the derivative of y squared is 2y, but since I took a derivative of a y part, I'd multiply it by dy over dx. The derivative of negative 5y is negative 5, but I took the derivative of a y part, so I multiply by dy over dx. I have a lot of dy over dx's. The derivative of negative x squared, that's just normal, negative 2x. Now, be aware here, the derivative of a number is 0. So that side's 0. Okay, I just took the derivative. You just took the derivative implicitly. Now, the other three steps in the process are just to get the, instead of having the dy over dx spread out between these three terms, okay, we're going to keep these three terms here and move this negative 2x over so it becomes positive 2x on this side. Switch sides, switch signs. And then I'm going to factor a dy over dx. That's the only thing I'm going to factor out. I might be able to factor more stuff out. I don't care. I'm just going to factor out only the dy over dx because that's what I'm trying to get by itself. So I factor it out. If I get rid of it here, I have 3y squared. If I get rid of it here, I have 2y. If I get rid of it here, I have minus 5. And over here, I just have 2x. Now, one step, it says get dy over dx alone. So since I factored it out, the operation between dy over dx in my quantity is multiplication. How do I get rid of multiplication? You just divide both sides by this whole mess. So you just take this side divided by this, cancel, and then I just write that whole thing underneath 2x. And the less you do to this, the more likely you are to keep it correct. The more weird stuff you try to do to this, you're probably wrong. Okay? The only thing that I might try to do is see if I could factor anything out of here, but I can't. Like factor a number or letters, you might factor the top and bottom and see if anything cancels. But that's your derivative. Yes, you're going to have x's and y's mixed up. So this is a formula for the slope of this function at any point. This is a formula for the slope of this function at any point. So I could find, let's say I wanted to find the derivative, find dy over dx at I have to make up an ordered pair for this, so. At 1, 1. So find the derivative at the ordered pair 1, 1. Okay? Well, that means that if you put 1 into this, you get 1 out. Okay? So they're saying this must be the dot on the graph of this. And so to find the derivative at that point, I just put 1 in for x and 1 in for y. That's all. So you can still find the derivative or the slope of this at a point. You're just putting the x value in for the x's and the y value in for the y's. So I think there's an example like that here. All right, now I want you to really pay attention to the next example There's always one like this on a test. So if I want to find this derivative, the difference when I take the derivative from left to right is that this term now is a product. This part requires the product rule. Okay, so I'm just going to say the first is x cubed, the second is y cubed. And just a little tip for other problems. Let's say I had like negative 10 times x cubed y squared, and I wanted to take the derivative of that term. It is going to be easiest to leave the negative 10 and think of using only the product rule on these two and then distributing the 10. That's going to make your life way easier. So think of just using the product rule on x cubed y squared and then distributing the 10. So you'd say first times derivative of the second plus the second times the derivative of the first. And then, like, this term can just become like 2x cubed y. You can just put a 10 in front of both terms. It'll just be a lot easier. Okay? Here we don't have a number to deal with. So I'm just going to use the product rule on this part. I'm going to skip a step so we know that's separate. All right, so x cubed is the first. Y cubed is the second, so I'm going to take its derivative. So 3y squared. Since I took the derivative of the y part times, you could use y prime. Here's using y prime. And then, so this is the first times derivative of the second plus the second times derivative of the first. So the second is y cubed. I didn't take a derivative, so I don't write y prime, times the derivative of the first, which is 3x squared. Now, don't forget to take the derivative of negative y, which is negative 1 times y prime. And then on this side, the derivative of x is just 1. So I tried to show you, like, these terms are from the derivative of that product rule. Negative y has that derivative, equals derivative of x is just 1. Now, do you see how this is a little bit harder to tell where the derivatives are when you use y prime? It's fine if you do that, but like these are the variables I need to like get these two terms on the same side. Like this is my dy over dx. Do you see how they can kind of get lost? It's okay if you do it this way, that's fine. You'll see this in the solution manual, but that's a reason, like, when I look at this in comparison, like that definitely stands out. Now, I'm going to have to do a little bit more work here to get the y primes alone, and it also helps, like, you need to recognize this is all one term, and this is actually, I would write this as 3x cubed y squared times y prime. And then I would write this term as 3x squared y cubed, and then I would just write this term. I would still write negative 1 y prime, 1 y prime equals 1. Okay, so this is just like cleaning up the terms a bit. Now, both of the terms with y prime are already on the same side. This term needs to go over here and become subtracted. So I'll have 1 minus 3x squared y cubed now. This goes away here. Out of the two terms that are left, I am only going to factor out a y prime. What I have left here is 3x cubed minus y squared, and what I have left here is negative 1. If you factor something out of a term, like let's say you didn't have the 1 written, some people think that if they factor out the y prime that they have 0 left here. That's wrong. Okay? When you have to distribute this and get two terms back. You can't get two terms if you put a 0 here. All right, now all I have to do to get y prime is divide this over here. So this is 1 minus 3x squared y cubed all over 3y cubed, or sorry, x cubed, y squared minus 1. Now these might look similar, you might think things cancel, but absolutely not. Okay, there is subtraction in the numerator and denominator. Okay, this is all one quantity. It would have to have an exact matching quantity in the denominator to cancel. Don't even try. And these aren't even the same powers on the x's and y's. Leave it. Leave it. The more you try to do at this point, the more likely you are to mess up a correct answer. All right, we have 2 more examples. Let's see how far we can get. So it says determine the slope of the graph here at this point. Now I want to make a couple comments about this because you might get problems that say determine the rate of change. It might say determine the rate of change instead of the slope. Slope is a rate of change. If any problem ever asks you to find the slope or the rate of change at a value, they're asking you to find the derivative first. So when they say find the rate of change of a function, it means you have to find its derivative first. When it says find the slope, you find its derivative first and then put the number in. Oh, okay. All right, so I'm not worried about this point at all yet. So first I'm going to take the derivative. Now this one is a little messy. Okay, so on this side I have to use the chain rule and the chain rule. The chain rule inside the chain rule. That's okay though. So first of all, the outer function is 3 times something squared. And the inner function is x squared plus y squared. So now if I take the derivative of the outside, it is going to be 6 times something to the first power, and that something is x squared plus y squared. Okay, I didn't actually take the derivative of y, so that's it. Times the derivative of the inside, I'm going to put parentheses because I'm going to end up with 2 terms. The derivative of the inside, the derivative of x squared is 2 times x. The derivative of y squared is 2 times y times dy over dx. Now please don't try to FOIL. Don't try to multiply all this out. It's not going to be worth it. Okay, I mean we might have to, but I might also not have to. Okay. Now on the other side I'm going to take the derivative, and this is an example of ignoring the 100. So when I take this derivative, I'm going to ignore the 100, and on the x times y, I'm going to use the product rule. So on the other side, I'm going to have 100, parentheses. All right, the first, which is x, times the derivative of the second, which is dy over dx. And you can just think the derivative of y is dy over dx. If it's just plain old y, its derivative is dy over dx. Plus the second times the derivative of x, which is 1. I'm not going to write times 1. Now, here's the deal. We probably are going to have to multiply this out in the long run because I do have a dy over dx on both sides. Okay? So, but here's what you need to know. Derivative. That's the derivative. That is the derivative. Calculus is taken care of. But now we need to do the manipulation to get the dy over dx alone. Okay. So, first of all, I'm going to ignore the 6 for now, but I'm going to FOIL. X squared times 2x is 2x cubed. X squared times this mess is going to be 2x squared y times dy over dx. Again, I'm just doing algebra. I'm doing FOIL. Okay, the inside is going to be 2xy squared And the last is going to be plus 2y cubed times dy over dx. Now all of that does need to get multiplied by 6 eventually. Here I'm going to distribute the 100. Now what I tend to try to do, like if I don't want to rewrite everything, is I'm only going to rewrite this side, okay? I mean, I guess I could leave the 6 out there, but no, I want to distribute it. So I'm going to get 12x cubed plus 12x squared y they're all 12s. And then I don't rewrite that side because I'm too lazy. Again, have we taken the derivative already? Are we doing anything calculus right now, really? No, just some algebra stuff. It's different algebra, right? Okay, now, do you see how this side has a dy over dx term? It's the first time we've had that. That's just going to move over, and what's going to happen to it? It's positive here. It becomes, it's just negative on the other side. Now, I tend to think these three terms need to be on one side. This one's going to change to negative, and I'm going to have to factor out the dy over dx. Like, it's the same every time. So, couldn't I just write dy over dx out in front? Like, skip a step. And then, if I get rid of the dy over dx here, I'll have 12x squared y. Took care of that term. If I get rid of the dy over dx term here, I'll have plus 12y cubed. When this moves over, it's going to be minus. I get rid of the dy over dx term there, and I have 100x. So I actually, in one step, I can do a couple different things. I can factor and get all the dy over dx's on one side. And again, that is the only thing you want to factor out. I don't care if you could factor out a 2 or a 4. Don't do it. You don't need to. Okay, you might do that later. Now, these two terms that don't have the dy over dx, they move over here with the 100y, but both of these turn into subtraction. Now, I just choose to write positive terms first, but the order that you write the 100y and minus each of these over here makes literally no difference. Okay? As long as you have 100y and then subtract this and subtract this on the other side, you're good. I would write it as 100y and then minus, and then minus, are you with me? Now, what's the last thing we have to do? Just divide by that. I don't write it divided on both sides. I don't even rewrite the top. I just cross this out and stick it on the bottom here. That's kind of how I show my work. Now, there is something we could do to cancel here, and it is kind of what I noticed, here, I could, what common factor could I take out of all the numbers on the top and bottom? 4. So I could factor a 4 out of the numerator. And a 4 out of the denominator. And then they would cancel. That's the only way you can cancel something, is if you can factor the same thing out of the top or bottom. Or the bottom just had if the bottom would have just had 4x squared or something, you could have canceled the 4's. Now, this wasn't the answer we were actually looking for. We wanted to know this derivative at 3 comma 1. The slope. What's the slope at 3 comma 1? Well, slope is rate of change. They're both derivatives. So we took the derivative. Now we're just going to put 3 in for all the x's and 1 in for all the y's. So if I put 1 in for the y's, you know, here it just becomes 25. 3 cubed is 27 times another 3 is 81. Here, that's just going to be 1, so 3 times 3 is 9. And you do have to work out all the top first. And then in the denominator, I mean, this is just like evaluate an expression, like the first day of Algebra 2. So now I'm just putting 3 in for the y's on the bottom, or the x's, and 1 in for the y's. So this becomes 9 times 3 is 27 plus 3 y cubed. 1 to any power is still 1. And then minus 75. We just work out the top. Negative 90 plus 25. (13/9). So the slope of that original function at the ordered pair 3 comma 1 is 13/9. Now I am making a video of this, so like if you miss something, I'll post it on Sioux City Schools Canvas. Maybe WIT, we'll see if that WIT will let. All right, we have one more example. Second derivative implicitly. So we want to find the second derivative. Well, you can't find a second derivative until you find the first. So first we're going to find the first derivative. So I have to use the product rule. This is again where I'm going to ignore the 4. And the derivative, the first times derivative of the second, plus the second times the derivative of the first, done, equals 0. Now, I could distribute the 4, but I could also just divide both sides by 4, and then it just goes away. Because 0 divided by anything is 0. It would eventually cancel if you just distributed it as well. Yes? The derivative of 10 is 0.
Okay.
Yep. All right, now to get dy over dx alone, I don't have to do any factoring. Now I just subtract y and divide by x. So dy over dx is negative y over x. And we're going to need this later. This is our first derivative. We were asked for the second derivative. So I just need to take the derivative of this. So now, using this notation, the second derivative, like, all I have to do, like, I just have to take the derivative of this side. And then the second derivative, d2y over dx2, or if you're using, or if you used y prime notation, this would be y prime prime, okay? So if you had it like this, x times y prime plus y equals 0, you got y prime by itself, you have y prime equals negative y over x, then you just write y prime prime and then take the derivative. Either way, it doesn't matter. What rule am I going to use to find this derivative? The quotient rule. Okay, now pay attention, the quotient rule. I'm not going to spell it right now. Okay, so we take the bottom times the derivative of the top. What's the derivative of negative y? Negative 1 times dy over dx. Same, works the same. Minus the top times the derivative of the bottom, which is 1. All over the bottom squared. Now, before I tell you that there's a problem, I'm going to rewrite this. I'm just going to clean it up a little bit. So, like, this is our second derivative. Like, this is our second derivative. our answer is just going to be like d2y over dx2 equals, but here's the deal. I can't have this. I have to get rid of it. Okay? I can do that by substituting dy over dx with this. Isn't that what we found dy over dx was? Okay, so I'm going to eventually substitute that in, but before that step, I'm going to do that step here. I'm just going to write this a little nicer, because x times negative 1, can't I just write that as negative x? Right? Isn't that just negative x? And then a negative times a negative is a positive. I mean, doesn't this look a little nicer? It's the same thing, okay? Now I'm going to change this into negative x over y. So I have negative x, parentheses, y over x plus y over x squared. Now multiply these two. What happens? The x's cancel. A negative times a negative is a positive. And then I can write my final d2y over dx2 as y plus y. Well, what's y plus y? It's 2y, like terms, over x squared. And that's my second derivative. So what can you look at to help you? PowerPoint presentation, videos from the online book. I know that there's a video link on the Google document too. And I made a video in case you wanted to rewatch it or watch a video. If you missed any of the pages here, I think I have most of them still. So if you needed to snap pictures of anything. So we won't be having a test, the test won't be next week, it's the week after, okay? So, but it is on a Monday or Tuesday, so, thank you.